One more example, and this one's a pursuit problem. We've seen what those look like before with constant velocity. Now we'll mess around with acceleration. Here we go. So we have a car, and we have a motorcycle, and they're going to race. They're going to go a total of 400 meters. And let's see what we've got. The motorcycle is going to start from rest. Motorcycles start from rest. And accelerates at 4.5 meters per second squared. The car, let's put the car in a different color. A little bit different of a color. The car is going to drive a steady 25 meters per second, but will already be up to speed when the race begins. So the car is going to start behind the starting line, going to take off, get up to 25 meters per second, and at the moment that it passes the starting line, that's when the motorcycle is going to take off. I want to know who wins. That's a little bit of a different question versus, hey, find this variable. But who wins when the speeds match who is ahead? So that looks like looking for an X final type of question. And who is ahead here? That looks like an X final kind of question also. Who wins? We can approach that one a couple different ways, so I'm going to get there. With a pursuit problem before, I made a table and I had the values that I usually wanted to use back then, which were X initial, X final, V. But now we've got acceleration, so I'm going to add in V final, acceleration, time, and we're going to set this thing up very much like we did before. So I've got these two columns. Over here I'm going to have the car, over here I'm going to have the motorcycle. And I'm going to fill in what values I can. For both of them, I get to pick where I would like to be x equals 0. I'm going to pick right where they start to be x equals 0. I'm starting the car at 25 meters per second. It's going to keep going 25 meters per second. It has an acceleration of 0. I don't know the time. I can figure out the x final part, and that's fine, but I'm going to leave this alone for just a moment. The motorcycle is going to start with 0 velocity. It's going to have an acceleration of 4.5 meters per second squared, and I know for sure that I don't know the final speed. Now if I'm looking for who wins, I can do this a couple different ways. I can start the problem by let me move this. I can start the problem by looking for who gets to 400 meters first. So I can put 400 meters here, 400 meters here, and figure out who is going to get there first. I could figure out how far they're going to be at the same time, which is maybe a different way of approaching it. Or I can say, what if I figure out where the motorcycle passes the car? So what's going to happen with this problem, I'm going to have something like this, and my motorcycle speeds up, speeds up, speeds up. Let me exaggerate that a little bit. Is going to speed up and do something parabola shaped, where my car is going to do a very steady speed. And somewhere or other, these are going to pass each other. Or the motorcycle is going to pass the car. When they get to the starting line, when the race is about to begin, the car flies right past the motorcycle. Motorcycle gets started. So the car will be ahead for pretty much the whole race. And then there will come some moment where the motorcycle passes the car. So a different way of answering this question is to say, where are they when that happens? If that's more than 400 meters, then that means that the car has already won, right? If my 400 meter line is here, for example, then the car passes before the motorcycle does. But if that happens, if my 400 meter line is up here, then the motorcycle passes before the car. So I want to know maybe where that is. I'm going to find where they meet. This is a pursuit problem, and with any pursuit problem, the big thing that we have, if we are finding where two things meet, they will be in the same place at the same time. And I think that's how I'd like to approach this problem. So I don't know where they're going to meet. I don't know when they're going to meet. But I know that what's true over here is going to be true over here. I have my kinematic equations. They look like this. And again, my first equation doesn't have information about v final. Second one doesn't have information about x. The third one doesn't have information about t. That's my starting point. For the car, I have an acceleration of 0. When I have an acceleration of 0, and I want to show you this, when I have an acceleration of 0, this first equation simplifies to that. Fine. Second equation simplifies to this, v final equals v initial. It's true, but it's not helpful. And the third equation simplifies to this. V final squared is v initial squared. Again, true, but not helpful. So as soon as I see an acceleration of 0 over here for the car, I'm going to use equation 1, because it's the only one that makes any amount of sense, that's any kind of helpful to me. So for the car, I'm going to use equation 1, and equation 1 is going to say x final equals x initial v initial t half a t squared. I have an x initial of 0, I have an acceleration of 0, and I'm going to label this thing as the velocity of the car. Fine, but I have two unknowns in this equation. I have x final as an unknown, and I have t as an unknown. I can't solve that. What I can do is mess around with this motorcycle. Now if I used equation 1 for the car, I'm going to use equation 1 for the motorcycle. I'm going to do that because I know for sure I'm going to have the same variables in there. Alright, for the motorcycle, again, that thing's 0, and my initial velocity is 0. I don't know x final, but I know that these two are equal to each other. I don't know t, but I know that these two are equal to each other because that's what a pursuit problem does. So now, if these are equal and these are equal, I have a system of two equations with two unknowns. I'm going to label this acceleration of the motorcycle just so I keep them separate. I have two equations with two unknowns. I'm going to set this equation, this top equation, equal to the bottom equation. When I do that, I'm effectively saying this stuff right here must be equal to this stuff right here, because this equals x final, and this equals x final. And if those x finals are the same, that tells me that this equals that. Here we go. I have v initial for the car times t. That's all that's left of that top equation. And on the bottom equation, I have half acceleration of the motorcycle times t squared. I'm going to cancel out 1t, and that leaves me with just the 1t over here, so I can solve for that. And I can plug in those values. 2 times the initial velocity of the car, which was my 25 meters per second, divided by the acceleration of the motorcycle. And that gets me a value of t equals 11.1 seconds. So I'm going to put that into my table. It's the same for both. So now all I really have to do is find where are they when that happens. I'm going to use this top equation just because it's a little bit easier. And what this top equation said was that x final equals the initial velocity of the car times the time. I know the time now, so I'm going to get 25 meters per second times 11.1 seconds. I don't know what that is off the top of my head, but it's definitely less than 400. That is 277.5 meters. That is the point where the motorcycle passes the car. After that, looking at my graph, after that, the motorcycle is going to be ahead for the rest of forever, which means the motorcycle wins the race. Back to the question. So who wins? Got that one taken care of. That was kind of the strange one to answer. When the speeds match, who is ahead? So we can actually answer this one without doing any math at all. One way, we talked about the slopes and a little bit about how the slope of the position versus time graph is the velocity, right? So if you have any amount of calc background, you might look at this and say, well, right here is where my tangent line matches clearly the car is ahead. But we can get there logic-wise even without doing any real math. The car is ahead of the motorcycle from the start, right? The car is moving 25 meters per second. For the motorcycle to catch up, it has to move faster than 25 meters per second. If the car is moving 25 meters per second and the motorcycle is moving 10 meters per second, the car is pulling farther away. When the car is moving 25 meters per second and the motorcycle is doing 24 meters per second, the car is still pulling away. Motorcycle speeds up just a little bit more, gets up to 25, the car is still ahead. Motorcycle gets up to 26, now it's starting to close the distance. Motorcycle keeps going and going and going and speeding up, and it closes that distance. In order for the motorcycle to catch up to the car, it has to move faster than the car at that time. When their speeds match, the car has to be ahead. So without doing any math, we can say definitively it has to be the car. And now, who is ahead when the car passes the 200 meter mark? We can do this one a couple different ways also. This point right here is at 277.5 meters. Before that point, the car is ahead. 200 meters, that's before, sorry I labeled this down here. This is at 277.5 meters. It took 11.1 seconds. Any distance before that, I know that the car is ahead. So at the 200 meter mark, the car is ahead. It gets there at an earlier time than the motorcycle does. So the car. I didn't have to do any math for that one either. By choosing how to answer my first question, how to approach my first question, I got the other two answers for free. Sometimes that's worth it.